So, so now we know that, as we said, fluid compartments, we have our intravascular, and our intravascular fluid is called plasma, and we also have our interstitial, and we also have our intracellular. So our intracellular fluid, we said it's called cytosol, and the fluid that bathes the cells, that is found around the cells, is called the interstitial fluid. Interstitial fluid. And the fluid that is found inside the vessels is called the plasma. It's called plasma. So we said that there's a constant movement of water between these compartments. It's also very important to note that what actually separates the intracellular fluid from the interstitial fluid is just one layer, a bilipid layer. It's a bilipid layer that separates these two. So it's easy for stuff to move from this side to this side and vice versa. So there's a movement of fluid from the intravascular to the interstitial and back. There's also a movement of fluid from the interstitial into the intracellular and vice versa. Now we need to look at what are the factors that play a role or that regulates this movement of water from one compartment to another. So, So the movement of water from the intravascular into the interstitial, that movement of water there is depends on a force called hydrostatic pressure. Hydrostatic pressure. Hydrostatic pressure is the pressure that is exerted by the fluid that is inside the vessels onto the walls, the endothelial walls. Because of that pressure, water starts to move through the endothelial wall into the interstitial space. This happens on the arterioles, through the walls of the arterioles, right? Now, the body cannot have a state whereby there's a lot of fluid that escapes from the intravascular out into the interstitial without correcting that. The fluid that moves out because of the hydrostatic pressure that escapes out of the intravascular into the interstitial space is later brought back by another force called the oncotic pressure. Oncotic pressure. It's important that whatever that we lose, we later gain it. Otherwise, we are going to have a pathology. Like, for instance, the pathology that results when there is too much hydrostatic pressure that has overpowered the oncotic, it means that water will accumulate in the interstitial, and that's called edema. That's called edema. Now, we know how the hydrostatic pressure occurs. It's because of the amount of fluid that is in the vessel that is exerting pressure against the endothelial wall, forcing fluid to escape into the interstitial space, into the interstitial space. Now, the oncotic pressure returns that water back into the intravascular. I mean, imagine if you've got, you don't have a force that counteracts the hydrostatic. That means that you are going to have a patient that has got intravascular depletion while they are accumulating edema on the other side. And also, imagine if you had oncotic pressure but you didn't have a strong hydrostatic. You are going to have a situation whereby water from the interstitial is drawn into the intravascular, depleting the interstitial fluid. And when interstitial fluid is depleted, you are going to have a problem, because this water from the intracellular will start moving outside because of the... We are going to talk about what determines the movement of water into and out of the cell. But you're going to have a water that moves from here, and then the water moves from here to here. Now you are having a situation whereby you are depleting your intracellular and your interstitial fluid just to replenish your intravascular. So that's also pathological. So you want a balance every time and any time. Static pressure takes water out of the intravascular into the interstitial, and that water is brought back into the intravascular by the oncotic. But there's a bit of fluid that the oncotic pressure is not able to take back, and that fluid accumulates there. I'm going to make an example. Let's say the oncotic pressure managed to take about 1,000 mils. Just making an example, guys, because there's a concept I want you to grasp. So let's say the hydrostatic pressure took about 1,000 mils of intravascular fluid into the interstitial, and the oncotic is only able to take back about 950 mils, which means you've got a 50 mils of water that will stay in the interstitial space. What happens to that excess fluid? Because if it keeps, if every time the hydrostatic pressure takes water into the interstitial space, you always have a remaining 50 mils every time, then that means that 50 mils will actually accumulate there and actually cause edema. So this is why you have the body has got another system to make sure that this water gets back into the circulation. And that happens through the lymphatic system. The lymphatic vessels. So this 50 ml will make it back into the heart through the lymphatic vessels, into the thoracic duct, and into the subclavian vein, and into the heart. So, which means now you can have a situation. So the lymphatic system is responsible to drain the excess fluid that the oncotic pressure could not drain back into the intravascular space. So it drains it directly into the veins, but not directly into the subclavian vein, later into the heart. So, which means when you've got, you can have edema when you've got excessive hydrostatic pressure, or when you've got a lymphatic pathology, say lymphatic obstruction. So you can still have swelling of the legs, right? And we know that the oncotic pressure is dependent on the amount of protein in the intravascular. So the proteins that you find there, and then they are the ones that are able to draw water back into the intravascular space. And the main protein that does this, as we all know, is albumin. So when you've got low albumin, hypoalbuminemia, you create a situation whereby you weaken your oncotic pressure. Once your oncotic pressure is weakened, then it means the fluid that was brought by the hydrostatic pressure will accumulate